Good evening to you, sir. Tonight I will present uh, a journal regarding hybrid control or compliance control. And this topic is the development and hybrid force position control of a compliant rescue manipulator, which was authored by uh, I think they are a faculty of the College of Engineering and Electrical Engineering from the Nanjing University of Aeronautics and Astronautics from the Jiangsu Province, Republic of China. And this article was received last December 23, 2016 and revised on May 13, 2017 and accepted on August 3, 2017. So 2017, it's 4 years. So introduction. In the last decade, large numbers of people have suffered from different kinds of natural or man-made disasters causing large scale of damages such as earthquakes, landslide, mining accidents, floods, and many others. After these disasters, it is of great significance to search the survivors in the ruins and provide necessary medical assistance and treatment as soon as possible. The surface survivors can be easily found and rescued in time. However, for the interior victims trapped inside the confined spaces under piles, it is difficult and dangerous for the responders and canine teams to execute the rescue and relief works due to the harsh or dangerous conditions. Therefore, more and more researchers have focused their efforts on developing rescue robots to explore deep under debris. And most of the existing rescue robots were designed with smart size, multiple joints, and strong crawling capacity to drill into small uh, crevices and assist victims. So, from the article, I think they have several related literature, but I only uh, include two related articles, related literature, which are Arai et al. And Kitagawa et al. For Arai et al., they develop a series of snake-like roller vehicles called Soryo for in-rubble searching operation. These robots were equipped with motors, cameras, and sensors, battery and control unit inside body, and remote operated via wireless joystick. The large cross-section area definitely limited its mobility within narrow space. And Kitagawa et al. Uh, from the reference 6 investigated a small-sized rescue robot named ActiveHost for searching the survivors within collapses. The ActiveHost, made up of eccentric war mechanism, was driven by several wound tube actuators and capable of swerving to arbitrary direction. The major drawback of this rescue system is the large friction between the robot body and external environment. So, as We can see from figure 1, the rescue robot system is mainly composed of a driving system located at the proximal end, a slender flexible tube with a diameter of 40 mm and a length of 3 meters, and an automatic insertion system consisting of a crawling mechanism and a pushing or and pulling mechanism, and a compliant manipulator mounted at the distal end of the cylinder tube. Also, a micro camera from the figure. So from the figure, a micro camera integrated with audio intercom system is installed on the front of the manipulator for the purpose of collecting the environment information and guiding the rescue operation. With that, the rescuer is able to get the view of micro camera from the monitor and communicate with the survivors through intercom to acquire their real-time conditions and requirements. And the food, water, fresh air, and emergency medicine can be transferred to survivors through the slender flexible tube. And in some situations, the manipulator needs to feed the survivors or even provide simple treatment to the injured victims. And figure 2 is the CAD model of the compliant manipulator. From figure 2A, we can see that it is an integral structure. For figure 2.B is the gripper, C is the bending component, D is the rotary component, and the gripper is driven by tendon 1 and sheath 1. The bending joint 1 is driven by tendon 2, tendon 3, sheath 2, and sheath 3. The bending joint 2 is driven by tendon 4 and tendon 5, sheath 4, and sheath 5. The rotary joint is driven by tendon 6, sheath 6, and sheath 7. And from the figure, the tendon sheath driven manipulator can be basically divided into 3 parts, which are the gripper, the rotary component, and the bending component. And the gripper will clamp and grasp the object if the tendon attached to the internal beam of gripper is pulled. On the contrary, because of the recoverable property of elastic deformation, the gripper will automatically open if the tendon is relaxed. The rotary joint plays a significant role during rescue operation. When the tendon is fixed on the groove of driving pulley spool, the rotary component is able to perform rolling movement in the range of positive and negative 90 degrees. The bending component consists of 2 C-shaped compliant bending units which are mutually orthogonal and can perform the yawing movement and the pitching movement in the range of positive and negative 45 degrees respectively. And from figure 3, it illustrates the photographs of the compliant manipulator performing different actions. This is from reference 19. So, from figure 3, we can see that A, for figure 3.A, is the grasping movement, B is the yawing movement, and C is the pitching movement, and D is the rolling movement. For the calibration and modeling of the compliant gripper, the sensing detection method and the kinematic and dynamic characteristics of the compliant manipulator are far more complicated when compared with those of the traditional rigid robot manipulator. And this paper, this article is mainly focused on researching the calibration method, modeling approach, and control strategy of the developed compliant gripper. For the purpose of measuring the gripper displacement and clamping force with the additional non-integrated sensors, two groups of high precision resistance strain gauges were attached to the large strain positions of the gripper. The finite element analysis, or FIA, of gripper was performed using SolidWorks or simulation software package to determine the target locations. The material parameters of a compliant gripper, which made of beryllium bronze, are specified as follows. Elasticity modulus is 128 GPa, yield strength is 1035 megapascal, density is 1260 kg per cubic meter, and Poisson's ratio is 0.33. So during FIA simulation or finite element analysis simulation, a pulling force with a value of 10 Newton was applied to tendon. The base of the gripper was set to immobilize, and the FIA result is shown in figure 4. As can be observed, the induced large strain positions occur around the inner ends of the gripper, which are marked as point A, point B, point C, and point D. The maximum stress is about 240 megapascal, which is smaller than the yield strength. And thus, to achieve self-sensing capacity, 4 strain gauge sensors are symmetrically arranged on these large strain positions of elastic beams, which are connected into a double arm bridge to compensate temperature variation and linearize output. From figure 5, the gripper with strain gauge is shown. The strain gauge group 1 is capable of detecting the displacement of the gripper, while the strain gauge group 2 is capable of detecting the clamping force. And two high precision pressure sensors were attached to the top and bottom surfaces of the clamp object to obtain the actual clamping force. Besides, a linear position sensor was connected to one of elastic beam of gripper. It should be noted that the force required to drive the push rod of the linear position sensor is less than 0.05 and thus can be neglected during practical operation. Calibration experiments were conducted to establish internal relations between the output signals from strain gauges and the displacement and clamping force of the gripper. The voltages of strain gauges 1 and strain gauges 2 were compared with the outputs of high precision position sensor and pressure sensor. The experimental setup of the compliant gripper control system was developed in the MATLAB or Simulink environment with a real-time workshop kernel as depicted in figure 6. From figure 6, the platform mainly consists of the following: a servo AC motor as the actuator, 2 industrial personal computers as the host computer, the real-time target, a tendon-sheath transmission system utilized to deliver the pulling force to the gripper with 4 strain gauge sensors, and 2 high precision pressure sensors. And last is the linear position sensor to measure the clamping force and displacement of the gripper. So this is figure 6. For A, figure 6.A is the schematic diagram, and figure 6.B is the photograph of the experimental configuration. In the calibration experiments, the calibration ranges of the strain gauge displacement sensor and force sensor are about 0 mm and 11 mm, and 0 Newton and 19 Newton with 20 sampling points. The calibration results are shown in figure 7A and 8A, where the actual gripper displacement and clamping force, which is vertical axis, are plotted against the voltages of strain gauges, which is the horizontal axis. It can be clearly observed that the experimental results show approximately linear relationship between the strain signals and the corresponding measuring parameters. The least square method was applied to conduct the multi-point linear fitting process. As a result, the following relationships hold. So for where x is equal to 8.23 v sub 1 minus 0.22 mm, which is the equation 1, and f sub z is equal to 12.31 v sub 2 minus 10.59 Newton, where x and f sub c denote the displacement and clamping force of gripper. V sub 1 and V sub 2 represent the detected output voltages. And the measurement with white noises of strain gauges with 0 voltage inputs with 5 seconds were acquired and depicted in figure 7b and 8b. Meanwhile, the histograms of the measurement noises were shown in figure 7c and 8c. So this is figure 8. The calibration results of the green strain gauge force sensor, where A is the relationship between voltage of strain gauges and the clamping force, and B is the time history and histogram of the noise of strain gauges 2. We'll now proceed to the system modeling and parameters identification. According to the existing literatures, reference 23 to 24, the compliant manipulating gripper system, including the compliant gripper and the tendon-sheath transmission system, can be simplified into a mass spring damper system with dynamic model as shown in equation 3. Mx as function of t plus bx as function of t plus kx as function of t plus p is a function of t equal to tau as a function of t, where t denotes the time variable, x denotes the displacement of gripper, m, b, and k represent the parameters of mass damping and stiffness of gripper respectively, and p is a function of t describes the lamp effects of system friction, and tau is a function of T's output torque of the driving motor. And in figure 9, it illustrates the Bode diagram of open loop frequency response of the compliant gripper, which describes the transfer from the input driving torque to the output gripper displacement. Where figure 9A is the frequency and the magnitude, and for figure 9b is the frequency and the phase degrees. From the magnitude and phase characteristics, it can be observed that dynamic model of gripper can be approximated as a second order linear model if the driving frequency is lower than 10 Hz. More specifically, the system contains a resonant peak around 6 Hz with a magnitude value of 28.33 decibels, and the magnitudes in the frequencies below 1 Hz are about 25 decibels. According to the experimental data at frequency lower than 10 Hz, the second order model can be well fit by using the discrete data fitting tool of MATLAB. And the identified dynamic model can be described by this equation 4, where M, B, and K represents the estimated parameters of mass, damping coefficient, and stiffness of gripper, respectively. The experimental results and fitting results are compared in Figure 9. It can be seen that the fitting results of the second order model matches the experimental results well in the frequencies lower than 10 Hz. For the frequency higher than 10 Hz, a higher order model is required to describe the dynamic model of the gripper. However, since the necessary bandwidth rescue operation is lower than 10 Hz, the developed simplified dynamic model can be applied in the control strategy of practical application. Let's now proceed to the control methods and experimental validation. And force control strategy. The control of the clamping force of gripper is realized by utilizing a cascade PID controller. PID is proportional integral derivative or proportional integral derivative controller, which is capable of responding to the external disturbance rapidly and improving trajectory tracking performance. And the schematic diagram of the controller is shown in Figure 10. The analog output signals from the strain gauges 2 are firstly filtrated via a Wiesel loop past analog filter with a cut-off frequency of 35 rad per second, and then converted into the clamping force value F according to the relationship shown in equation 2, and finally compared with the desired force F times D. So this is a Figure 10, the schematic diagram of the cascaded PID controller for clamping force. The selected control parameters of the cascade PID controller and PID controller are presented in Table 1. The results of force tracking experiments with different control strategies are compared and depicted in Figure 11A and B. As can be observed, the tracking performance of the cascade PID controller goes much better than that of the PID controller. The histogram of the force tracking errors with cascade PID controller is plotted in Figure 11C. The results of force tracking experiment demonstrate the efficacies of the strain gauge force sensor and the cascade PID controller. This is Table 1 and Figure 11. Table 1 is the parameters of the cascade PID controller, and Figure 11 is the results of force tracking experiment, the comparisons of desired trajectory and experimental trajectory. B is the time history, and C is the histogram of the force tracking. Position control strategy. In this section, if SMC law is proposed, if SMC stands for fuzzy sliding mode controller, is proposed to regulate the displacement of gripper. The control objective is to develop an applicable robust control strategy with favorable performance, so that the gripper can follow expected reference position trajectory under undesirable influence of bounded uncertainties. From equation 3, we can define it into equation 5, where E sub P is equal to 1 over M, B sub P is equal to negative B over M, C sub P is equal to negative Q over M, and D sub P is equal to negative P over M. Considering that equation 5 with unpredicted model, parameters are entities for actual gripper, the system dynamic model can be written as equation 6, where L sub T is equal to delta E tau is a function of T plus delta Bx T plus delta Cxt plus dP is a function of T, which is equation 7. And L sub T denotes the lump uncertainty whose boundary is assumed to be given as L sub T. Absolute value of L sub T must be less than N, where N represents the predetermined positive constant. A sliding model controller with a PED sliding force surface is developed to enforce the system state trajectory to approach to the sliding surface and ensure expected closed loop control performance and specifications. The position, velocity, and acceleration tracking errors are defined. E is a function of T is equal to X sub D, function of T minus X as a function of T, equation 9. And E is a function of T is equal to X sub D, it's a function of T minus X is a function of T. So that is the position and velocity. If it is a double dot, it means acceleration. If single dot is it means velocity. Where X sub D is a function of T, dot xd is a function of T, and double dot xd is a function of T are described as are the desired position, velocity, and acceleration. And the switching function of the sliding surface is defined in the state space R square and expressed as the following equation. Is a function of T. This is equation 12. And for the expression for the derivation of the sliding variable can be shown as equation 13. Then inserting equation 6 and 11, we can now derive equation 14. In the conventional design of SMC system, the control loop U is a function of T is basically composed of two terms. The equivalent control term UEQ as a function of T, and the heating control term U sub heat is a function of T, and can be represented in the general form as follows. U is a function of T is equal to UEQ as a function of T plus U heat sub heat as a function of T. And the equivalent control term UEQ is a function of T, which determines the dynamic performance of system on the sliding surface, can be derived as the solution of is a function of T equal to 0 without considering any lump uncertainty. Thus, from equation 14, we can get equation 16. And the heating control term U heat is a function of T should be applied to eliminate the effect of perturbations and drive the system toward the reference trajectory. However, it may lead to heavily chattering phenomenon and high frequency and model dynamics. Thus, in order to mitigate the undesirable chattering problem, the heating control law is realized by using fuzzy logic inference mechanism. And the overall schematic diagram of the FSMC fuzzy sliding mode control is illustrated in figure 12. So this is figure 12, the heating, the schematic diagram of FSMC strategy for gripper displacement. The heating control law can be represented as U sub heat as a function of T is equal to Fs as a function of S as a function of T, where C denotes the proposed nonlinear fuzzy controller with a sliding variable is as a function of t, and the heating control term u heat as a function of t as the input linguistic variable and output linguistic variable respectively. And the center of gravity method is chosen as the diffusification strategy to compute the output variable of fuzzy logic. In guarantee high control sensitivity to the changes of input signals and meanwhile avoids time-consuming calculation process, the output value can be calculated as follows. U sub heat is a function of t is equal to the summation of r sub g r sub g from g equal to 1 up to 3 over the summation of e as a function r sub g, where g is equal to 1 up to 3, which is equal also to r sub 1 e times r sub 1 plus r sub 2 e r sub 2 plus r sub 3 e sub 3, which is equation 18. And from the above analyzing results of different situations, it can be observed that 0 is less than e sub t, e as a function of r sub 3 minus e as a function of r sub 1 is equal to e as a function of t times the absolute value of e times r sub 3 minus e times r sub 1. Furthermore, the entire control law shown in equation 15 can be represented as u is a function of t is equal to u eq as a function of t plus r times e times r sub 3 minus e times r sub 1, equation 19. For the purpose of demonstrating the system stability with the proposed FSMC scheme, the following I don't know how to pronounce this word, Lyapunov or Lyapunov candidate function is proposed. So this is equation 20, which is v sub t is equal to a square as a function of t over 2. And differentiating as a function of t with respect to time and utilizing equations 14, 16, and 19 gives the equation 21. And for the hybrid force position switching control strategy, in order to perform a completed manipulation task, the handling procedure of the compliant gripper falls mostly into 3 steps. First is the closing, second is the clamping, and third is the opening step. In the duration of closing step, the gripper is driven to approach to the object and execute the grasping action. It comes to the clamping step after the target object contracts with the gripper and is removed to a desired location. The opening step occurs after the object is loosened and placed on the destination. In this phase, the clamping force decreases to 0, while the gripper displacement is reduced under the tendon-sheath actuation. The position control performance is crucial to the closing step and opening step, while the accurate force control strategy should be executed during clamping procedure. Therefore, a hybrid force position switching control strategy is proposed to ensure smooth transition between different working steps and achieve satisfied control results, as is illustrated in figure 16, which is the schematic diagram of the hybrid force position switching control strategy. And for the results of the hybrid force position tracking control experiments, figure 17a is the gripper displacement tracking result. Figure 17b is the displacement tracking error. Figure 17c is the clamping force tracking result. D is force tracking error. E is the relationship between gripper displacement and clamping force. So these are the references for this article. Uh, thank you for uh, listening. That's all.